Good day, viewers. This is Afia Demola Johnson, your chemistry and biology tutor. Now, don't forget to share this video, to like it, and to subscribe. And don't forget our physical lectures at Christ Rock Academy by 5:30 to 7:30 p.m. Monday to Friday. Christ Rock Academy is located at kilometer 8 Sapley Road at Total Junction. Let's go where we take care of coaching of students for WAEC, for NECO, for JAMB, for post-UTME, for entrance into nursing science, and there is 24 hours power supply, and the environment is very conducive. So let's go on and look at geometric isomerism. Geometric isomerism. Under the topic isomerism. When we're talking about geometric isomerism, this is the occurrence of just two organic compounds. The occurrence of two organic compounds with the same molecular and structural formula. But different position of two similar higher groups. Two similar higher groups around two adjacent carbon atoms. Two adjacent carbon atoms which are connected by carbon to carbon double covalent bond. Now, so by the time I will be using examples, then you will understand what I'm talking about here. So there are two isomers. There are two geometric isomers. There are two geometric isomers. These are, we have 6 geometric isomer. And number 2, we have trans geometric isomer. Now, what do we mean by 6 geometric isomer? 6 geometric isomer. 6 geometric isomer. Now, this is an isomer in which the two similar higher groups are located on the same side. They are located on the same side of the two adjacent carbon atoms. The two adjacent carbon atoms between which the carbon to carbon double covalent bond exists. Now, common examples of 6 geometric isomers are, we have number 1, 6, 1, 2 dichloroethene. Now see what I'm saying here. Yes, for you to understand these two definitions I'm giving you, you must understand that for geometric isomerism, the compound must contain, the first condition is that there must be carbon to carbon double covalent. Between two carbon atoms, there must be a double covalent bond. And here now, this is carbon number 1, carbon number 2. Then chlorine here, that's how we have. Then hydrogen here, hydrogen here. So all we can also have carbon to carbon this. The chlorine can decide to be downward. So but the thing is that around these two adjacent carbon atoms, the two higher groups which are chlorine are on the same side, either up or down. So and that's why their name is what? Cis. That is, chlorine is attached to carbon number 1 and carbon number 2. That's 1, 2. Di means you have 2 chlorine. Dichloroethene. Ethene, 2 carbon is eth. Then E means what? The surface name for the double bond. Another example is cis-but-2-ene. Now if you are to write but-2-ene in the first place, but has 4 carbon atoms. Then this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. So the double bond must be between carbon number 2 and 3. That's what makes it but-2-ene. So then supply your hydrogen, 1 hydrogen here. Don't forget the carbon atom will be surrounded with what? 4 bonds. So that's why you have 1, 2, 3, 4. And you have this is 1, 2 bond in the front, 1 at the back, so you need 1 more hydrogen down. So you have 1, then you not put anything here again. You have 1, 2, 3 here, so you can put 1 hydrogen here. So this one already has 1 bond at the back, so you need 1, 2, 3 to make it 4. So this is real but-2-ene. But to convert it to the condensed formula, this one can be written as what? CH3, then CH, then double bond, then you have CH, this H, then you have what? Another CH3. These two CH3 are the 2 higher groups. You can decide to push them up. You have this. Why are we pushing them up? Don't forget, go and watch the video of hybridization that we did. The bond angle in the planar structure of alkane is always 120 degrees. So 120, 120, 120. And now on a straight and at a point is what? 360 degrees. So that is why it must be. So when it is pushed like this, or you can decide to have it as this, you can decide to have something like this. Then the hydrogen is up and the CH3 is down. CH3 here, another CH3. So what we want to achieve here is that these 2 higher groups are on the same side, are either on the upper side of the 2 carbon atoms bearing double bond, or they are at the lower side of what? 2 adjacent carbon atoms separated by a double covalent bond. Now let's look at more examples. Okay, number 3. We can also have cis-butene-dioic acid. Butene-dioic acid. That one, the first condition is that there must be 2 carbon atoms having double bond. Then we can decide to have COOH here, COOH here, and 1 hydrogen here, 1 hydrogen here. These are the 2 higher groups on the same side of the 2 adjacent carbon atoms separated by a double bond. You can decide, or you can also have it as HOOC. Then you have a double bond here, another HOOC. Then you have hydrogen there and hydrogen there. Why are we not saying COOH? The bond is between carbon and carbon. So if I come here and write COOH, I am saying that the bond is between carbon and hydrogen. No. So you have to rewrite it as what? HOOC, so that it is carbon to carbon, just like you have carbon to carbon here. So that is that. So then another example that we can have, you can have X 6x3 in. 6x3 in. Don't forget that hexene. You have 1, 2, 3, 4, 5, 6. 1, 2, 3. You have a double bond here. So then you have hydrogen, hydrogen. So this is hydrogen, 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 and hydrogen. So here you have hydrogen and hydrogen, 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 and hydrogen. So the bond line notation will now be what? CH3, CH2, then to what? To this. Then you have double bond. Then you can have CH2, which is this. Then CH3, which is this one. Then don't forget there's hydrogen here. So we can decide to push. These are the two higher groups now. CH3, CH2, CH3, CH2. So we can push it up now. CH3, CH2 can be up. Then this is the carbon atom. These two carbon atoms. Then H, this H is pushed like this. Then CH3 to CH3. Now will be here. Then hydrogen will be here. Or we can decide to have this is the first condition. Then we have hydrogen here. We have hydrogen here. Then we have CH2, CH3 here. Then we have CH2, CH3 here. So those are they. Then let's look at trans geometric isomers. Trans geometric isomer. Now, in the case of trans geometric isomer, the two higher groups are on opposite sides. They are on opposite sides of the two adjacent carbon atoms bearing the carbon-to-carbon double covalent bond. So now, what are we saying? Now, this is an isomer in which the two similar higher groups are located at opposite sides. They are located on opposite sides of the two adjacent carbon atoms separated by a double bond, double covalent. So examples are number 1. Just like we have cis 1,2 dichloro, we see about trans 1,2, trans 1,2